Today we discuss section 3.5 linear functionals. Linear function is nothing but a linear transformation f from v to f. This since this f itself is a vector space, you can consider set of all f from v to f, linear transformations from v to f. F is linear. This set can be represented by LVF. So this is the notation for set of all linear functionals. For example, first we discuss example 18. In 18 we have f of our v is a set of all n-tuples fn. So this is our v. V is our fn, and v is a vector space. V is equal to this, and f is our w. Then we consider this lvw. That means lvf. So we define f linear transformation from fn to f. Say f x1 etc. xn is equal to a1 x1 plus etc. an xn, where this a1 a2 are all elements of f. They are fixed scalars. Then you can easily prove that this is a linear transformation, because if you define a basis 1 for is a basis of f, then you can treat this as n-tuple a1 etc. Okay. Because this f of 1 0 0 is equal to a1, that is a1 times 1 plus 0 etc. So what is f0 1 0, that is a2 etc. f0 0 etc. 1 is equal to a. Okay. Now if you consider f of an arbitrary element x1 as xn, that can be written as if we consider this as epsilon 1 and this is epsilon 2, the standard basis, then you can write this x1 xn in terms of epsilon 1 epsilon 2 etc. epsilon n. That is this is summation xi epsilon I or xj epsilon j. So this is our xn. This j varies from 1 to n. Now this is our f of x1 x2 etc. xn. Then this is nothing but summation j is equal to 1 to n xj f of epsilon j. Because this f is linear, f is a linear transformation, then you can distribute this to this xj epsilon j, that is equal to this is same as summation j is equal to aj summation j from 1 to n aj xj. Okay, this is the definition of this. Okay, this is in the summation form. Now you can prove this f is linear using this f of the summation j xj epsilon j plus summation j yj epsilon j. So these are xn x1 x2 etc. xn plus y1 y2 etc. yn. Then this is equal to, this can be written as f of summation j xj yj xj plus yj times epsilon j. So this is equal to by definition this is same as summation j summation over j xj plus yj f of epsilon j. Okay, but this is you can write this as summation over j xj f of epsilon j plus summation j yj f of epsilon j. Okay, so this will give f of, this is equal to f of alpha plus f of beta, where alpha is equal to this x1 xn and this beta is equal to y1 by 2 yn. So similarly you can prove this scalar multiplication also. Then this f of x1 xn is equal to a1 x1 plus etc. an xn is equal to this a1. This can be treated as a1 a2 etc. an, because this function depends only on this this as far as x1 x2 is fixed, this the image depends only on this a1 a2 etc an. Okay, or otherwise you can say that this f of epsilon 1, f of epsilon 2 etc, f of epsilon n. So these are the fixed quantities. So any image of any this x1 x2 xn can be written as the can be written in terms of the images of epsilon 1 epsilon 2 etc epsilon n. That's why we use you can write this can be written as the matrix a1 a2 etc an. So as far as this x1 x2 xn is fixed, okay, otherwise this will vary. So this is an example for a linear function. Then we have another example. If we consider M and F set of all n by n matrices over F, then we define for A belongs to M and F, the linear function as f of A as trace of A. So this is an example for another linear transformation. F of A is equal to trace of A. Then you can easily prove that f of A plus B is equal to trace of A plus B, but trace of A plus B is equal to trace of A plus trace of B. Okay. So this will give f of A plus f of B. Similarly, f of C times A is equal to trace of C times A, that is C times trace of A. So this proves the definition of linear transformation for this f. This is C times f of A. Now we have another example that is similar to the some evaluation map, that will be the space of all polynomial functions from the field f into itself, and t be an element of f. Okay, for an element t belongs to f, we define a linear transformation from the set of all polynomial. If this is p of x is a polynomial, then lt of p of x is defined as p of t. So this is the evaluation of this p at the point t. So this will give a linear transformation from the set of all polynomials to f if t belongs to f. So if this lt of c times p of x plus q of x, you can write it as that is equal to, by definition, this is c times p of t plus q of t. Consequently, this is c of l c times lt of p, that is this one, plus lt of q, lt of q of x and lt of p of x. So this is another example for linear functional from set of all polynomials to the corresponding function. Another example is this integral function, this L of g. If we consider CAB, set of all continuous function on AB, then define a linear map, define a mapping from a set of all continuous functions on AB to real numbers, that is L of g is equal to, g is any continuous function, define the image of g as integral a to b g of t dt. Then you can easily prove that L of c times g1 plus g2 is integral a to b c times g1 plus g2. Then that can be, this integral can be distributed over the addition. So you can write that as this L of g c times g1 plus g2 is equal to integral a to b c times g1 plus g2 of t dt. So this can be distributed, that is this can the summation property is there, that is integral a to b c times integral a to b g1 of t plus integral a to b g2 of t with respect to t. So this will be c times L of g1 plus L of g2. So this L is also a linear function, linear functional from set of all continuous function to real numbers. Now this is the notation for set of all linear functionals on V, that is denoted by V star, and it is called dual space of V. Okay, so this is a remark. Please note this. If we say vector space, then set of linear functionals on V, that is set of linear transformation from V to the corresponding field F. Okay, that is normally that is denoted by LVF, and now onwards we discuss that LVF as V star. So that is called dual space of V. Now we can easily see that this dimension of V star is same as dimension of V, because dimension of LVW is defined as we have proved that this is dimension of W into dimension of V. Okay, so by we have already defined the basis vectors for LVW, say EPQ, EPQ of alpha J is this is EPQ of alpha J is defined as these are the dimension of W into dimension of V, linear transformations from V to W, and I'll write the explicit formula for this. If what is E11, E11 of alpha 1 is equal to beta 1, if alpha 1 I choose two bases, B is equal to alpha 1 etc. alpha n is an ordered basis for V and B prime, that consists of the vectors beta 1 etc. beta m, that is a basis vectors for W. Then dimension of W LBW will be m times n. That can be seen by choosing this basis vectors. E11 of alpha 1 is equal to beta 1. Similarly, E1 of alpha 2 is equal to 0, etc. E1 sorry, this is E1 1 of alpha n is equal to 0. Similarly, E21 of alpha 1 is equal to beta 2. Then or you can define E12 again. This is E1. This is a one linear transformation. This defines a linear transformation from V to W. Because if we choose a basis vector for V and any vector, any n vector from W, you can construct a unique linear transformation. That is E11 here. Similarly, you can define E12. E12 of alpha 1 is equal to 0, and E12 of alpha 2 will be this beta 1 again. And last one, E12 of alpha n is equal to 0. Similarly, using this beta 1 itself, you can define n linear transformations. Similarly, you can define n linear transformation using B2, beta 2, beta 3 and all. So we have mn linear transformation. So we can consolidate the definition of this E11, E12, etc. In this manner. This will be, the image will be beta p if that this is beta 1 when this coincides with this one. Okay, so we write it as if these two quantities are same, that is delta ij, delta iq, so delta jq is delta jq times beta p. That means whenever j coincides with q, we have beta p. Okay, then otherwise 0. Okay, so this is the definition. So I will write it as this beta p holds when q is equal to j, when q not equal to j, we have 0. So this can be written as delta jq beta p. Okay, so these now we have this p and q varies over p varies from 1 to etc. M and q varies from 1 to etc. n. Then we have mn elements are there. These are the basis vectors for LVW. We have already discussed this in the previous sessions of this chapter. Then the similar discussion will follow if you replace this W by corresponding field F. The only difference is if you replace this W by the corresponding field F, then the only possible element in this set is 1 or any non-zero element. This B prime will be a singleton set. Then this m will be 1. Consequently, this dimension of W will be 1. Then dimension of this, that this is the dimension of V star, V star is defined as LVW, then dimension of V star is same as dimension of V. That we have discussed in this. Dimension of V star is always same as dimension of V. Now, we can consider the basis EPQ, in case of LVF. Okay, so for that we consider a basis alpha 1 etc alpha n. This is the basis of V, and we have B prime. B prime consists of only one vector, that is beta 1 itself. Beta 1 is 1. This is a basis for F. Using these two bases, you can construct this EPQs. Okay, so here this Q is one. The possibilities of Q is only one, and the possibilities of this PR 1, 2, 3, etc. n. So what are the functions? So if we define f1 of, similarly we write that as EP1, that is E11 of 1, E11 of alpha 1, E11 of alpha 1 is equal to 1, and E11 of alpha 2 equal to 0, E11 of alpha n equal to 0. Similarly, you can define E21 of alpha 1. There is only one possibility for the second component, then there is only one always. E21 of alpha 1 is 0, and E21 of alpha 2, this is 1. Sorry, the second possibility is always varying, but the first component is this P is the only possible variation of P is 1. Okay, I'll write it as this P varies over this, and Q varies over 1, 2, 3, etc. n. Because we were considering this is the basis for V, and this is the basis for W, then we call the basis vectors of W as beta 1 etc beta m. So this m is 1, and if B is this alpha 1 etc alpha n, then n is n here, and m is 1. So this the variation of P is 1. So we can write the next element as E12 E12 of alpha 1 equal to 0. Similarly, E12 of alpha 2, we have these two suffixes are same, so we call the beta 1. Beta 1 is, this is our beta 1. The only possibility is 1, then this is 1, and the last one E12 of alpha n is equal to 0. And similarly, the last one you can define E1n of alpha 1 equal to 0, E1n of alpha 2 equal to 0, and E1 n of alpha n. Here the suffix this n and this n are same, then this will be 1. Then you can define n linear transformations from V to F. Okay, and we call this linear transformation as F1, and this is F2 etc. This is Fn. Then the definition is F1 of alpha 1 equal to 0, and other F1 of any other alpha to alpha, sorry, this is 1, and any other alpha 1, alpha to alpha 3 will be, image will be 0, and so on. And similarly, this F1 of F2 of alpha 1 equal to 0, only the F2 of alpha 2 is 1, the rest of them are 0. Similarly, in case of Fn, Fn of alpha n equal to 0, the rest of them are Fn of alpha n is equal to 1, and rest of them are 0. So this is what we call the basis corresponding to the basis B. Okay, B and B prime consists of only 1. Then this is the analogous basis of this EPQ in V star. So this is the basis of, so this F1, F2 etc. Fn is a basis for LVF. What is LVF? LVF is V star, the dual basis of V. Okay, so this F1, F2, Fn can be constructed from the basis b alpha 1 alpha 2 alpha n. So the basis, this f1 f2 fn corresponds to the basis alpha 1 alpha 2 etc alpha 1. So we call this is the basis for v star, that is the basis for a dual space. Then this is what we call dual basis. Dual basis of this basis, because this dual basis is constructed using the basis b. So this f1 f2 fn defined in this manner is called the dual basis of the basis b of v. Okay, now if we consider any f belongs to this v star, that is lvw, lvf, then this f can be written as c1 f1 plus etc cn fn, because this f1 f2 fn is a basis. We denote this as b star. This is the dual base of b, etc c and fn. Any element can be written as a linear combination of the basis vectors. So f is equal to this. Then this the meaning of the statement is f of alpha is same as c1 f1 of alpha plus etc cn fn of alpha. This is the meaning of this statement. This is for any alpha belongs to v, because these two are the two functions from v to f. Then in order to get the equality of two functions, you need to verify the images of these two functions at every point of v for the domain. So this is the meaning of this statement. So whenever you write this, you can get this. In particular, if you evaluate f of alpha 1, okay, what is f of alpha 1? F of alpha 1 is c1 times f1 of alpha 1. f1 of alpha 1 is equal to 1 and f2 of alpha 1, but f2 of alpha 1 is 0, so the rest of them are 0. Then you can get this as c1. Okay, c1 is f1. Similarly, what is f of alpha 2? F of alpha 2 is c2, etc. f of alpha n is equal to cn. Clear? So once you write the f is equal to c1 f1 plus etc fn, that is, once you write this f is equal to summation I equal to 1 to n ci fi, then the ci can be extracted from this expression itself. That ci is nothing but f of alpha I, because c1 is f of alpha 1, c2 is equal to f of alpha 2, and so on. So this will be summation I equal to 1 to n f of alpha I times fi. Okay, so any f can be written as f of alpha I times fi. Okay, so what we call these ci's. Okay, this f can be written as a linear combination of elements of b star. Then the coefficients are termed as the coordinates of that element. Okay, so this c1 c2 etc. If you write this the coordinate of f, this is an element of some vector space, say v star. Then what is the coordinates of f relative to the basis b star? Okay, so that is obtained by, that is nothing but c1 etc cn. Okay, but this c1 c2 cn are obtained from this equation. So that is same as, that is the coordinate of f relative to the dual basis b star is nothing but f of alpha 1 etc f of alpha n. Okay, so this is nothing but the images of this alpha 1 alpha 2 alpha n under the function f. So in order to get the coordinates of f, you need to evaluate that function at every basis point. Okay, so this here this b is alpha 1 etc alpha n. Okay, so this is the interesting connection between b star and b. So this is theorem 15. F can be written as summation I equal to 1 to n f of I alpha I. This fi is a dual basis for alpha I. Okay. So in the similar way, you can write this any alpha belongs to the vector space V that this since alpha 1 alpha 2 alpha n is a basis, then this alpha can be written as some x1 times alpha 1 plus etc xn times alpha n. Okay, now when you how you extract this x1 extraction, that is another point. Then if you evaluate this fi, if you replace this if you find the image of alpha under fi, then you can get this is fi of alpha. Fi of alpha will be fi of this quantity. So if you first you write this f1 of alpha, then you can get x1 f1 of alpha, okay, plus 0, because f1 of alpha 2 f1 of alpha 3 are all 0. Since this is a dual basis, then this will be x1, because f1 alpha 1 is 1. Similarly, that is f1 of alpha is equal to x1, f2 of alpha is equal to x2, and so on. Fn of alpha is equal to xn. Okay, so once you write this this alpha is a linear combination of alpha 1 alpha 2 alpha, and then this xi's are nothing but fi of alpha. Okay, so then you can write it as any alpha can be written as what is that x1, that is f1 of alpha times alpha 1 plus etc fn of alpha times alpha n. So any alpha can be written as summation I equal to 1 to n fi of alpha times alpha I. Okay, so these are the interesting connections between a dual basis and basis. So this proves theorem 15. Then we can see some examples illustrating these ideas of dual basis. Please do that. And next class we will discuss hyperspaces and null spaces of a linear functionals and the connections between those two.